Cramer's rule is like an application of determinants. We're going to work out three different determinants here, and we're going to use them in a couple of different ratios to figure out what the solution to a system of linear equations is. So let's start with the system of linear equations, and I'll show you the steps. Cramer's rule really is just an algorithm. We could prove it, but I'm not going to take the time to do that here. I really just want you to have seen this algorithm, and we can use it then to work out some solutions to systems of linear equations. One of the things to keep in mind as we do this is that the system of equations we're working with, the one we're looking for the solution for, has to be a system of n equations with n unknowns. What that means is it might be a system of two linear equations with two unknowns, x and y, or it might be a system of 5 linear equations with 5 unknowns. But I can't use this with a system of linear equations where there's 3 equations and only 2 unknowns, or where there's 2 equations but there are 3 unknowns. It won't work then. But if I have the same number of components in my solution, say x, y, z, as I do equations in my system, then Cramer's rule will work. Okay, here's a system of 2 linear equations with 2 unknowns. I'm using x and y here because I only have a very simple system, and I want to try to keep the notation as simple as possible so that we don't get too confused. Ideally, I would use x1 and x2 for my variables, but in this case, I'll just stick with x and y. Now, we can solve this system very simply. Let's start by multiplying the second equation through by 3. That lets me cancel these two terms. If I add these two equations together, those two terms cancel. I end up with 5x equals 15, and so of course x equals 3. One of my equations originally was x minus y equals 5, and if I plug 3 into that, I get 3 minus y equals 5, and then I'll subtract 3 from both sides, and negate the equation. So I have a system whose solution is x equals 3, y equals negative 2. Remember from algebra that this is a point on the plane where the two lines represented by the original two equations where they meet. So I can write that solution as 3 comma negative 2. I can also write it as a row matrix. Oops. 3 comma negative 2, or as a column matrix. So there are different ways to write the solution. But that's not the point of this video. The point of this video is to show you a different technique. And I've done this problem using standard algebraic methods, partly because it's so easy to do, but also so that you'll be convinced when we get to the end of the new technique that it actually works, because we'll end up with the same answer. Here's how Cramer's rule works. We're going to start by making a matrix of just the coefficients in the original system of equations. I'm going to call this matrix A. I'm also going to create two other matrices. I'm going to call them A1 and A2. Here's how we're going to make these. I'm going to take a copy of matrix A and stick it here, and I'll take another copy and put it over here. And then to create A1, I'm going to delete column 1. To make A2, I'm going to delete column 2. And I'm going to replace those columns in both cases with the constant column from the original system. So that's going to be, remember, this used to be just x minus y equals 5. So I'm going to have a 0 and a 5 here. Let me use a different color. A 0 and a 5. And a 0 and a 5. So it's the same two constants that come from the original system of equations, the 0 and the 5 from here. This used to be a 5. For A1, I've erased column 1. For A2, I've erased column 2, and I've replaced both of those with the constant column from the original system. Now I'm going to find the determinants of all three of these matrices. The determinant of A is -2 minus 3. The determinant of A1 is 0 minus 15. And the determinant of A2 is 10 minus 0. The solution to the system is x equals the determinant of A1 over the determinant of A. And for y, it's the determinant of A2 over the determinant of A. In both cases, the determinant of A we said was -5. The determinant of A1 was -15, and the determinant of A2 was 10. That gives me 3 for x and -2 for y, which is exactly what I got when I did it the other way. Now this is a little tedious for a 2x2 system, a system of 2 linear equations and 2 unknowns. This original algebraic method is actually really much more straightforward. But if you have a system of 3 equations and 3 unknowns, or a 5x5 system, Cramer's method can actually be a lot simpler, especially if the determinant is easy to figure out. It might be argued here that this is a good reason for using subscripts instead of XYZ, using X1 and Y1. Everything I've done here is kind of numbered. If I had an X1 and an X2, X1, X2, X1, I won't do them all, but you'll get the idea. This is X1, this is X2. Then down here, I would have an X1 and an X2, and I get X1 from the determinant of A1, and A1 came from deleting the first column, column 1. So this might not be a terribly compelling reason for using subscripts instead of XYZ, but it's one of several. In the next example, I'm going to use Cramer's rule to find the solution to a system of 3 equations and 3 unknowns. And there I could use x, y, and z, but I'm going to use the x subscript notation, x1, x2, and x3, because I think it'll just help clarify things even further. Okay, here's our 3x3 system, and we're going to start by turning this into a matrix. But we don't want an augmented matrix here. Remember, we're going to use the constant column here for something else in a few minutes. All I want is the coefficient matrix, and I'm going to call that coefficient matrix A. So I get something that looks like this: -6, -5, -3, -4, 2, 4, and -1, 0, 0. That's matrix A. Now I'm going to make 3 copies of matrix A this time because I have 3 variables. So I'm going to need to do this process 3 different times. There's one copy. Here's another. And here's a third. And in each one of these, in turn, I'm going to replace one of the columns with a column made up of the constants. Let's actually start by labeling these matrices. We have A1, A2, and A3. And then I'm going to remove the column in each one associated with its subscript. So in A1, I'm going to remove column 1. In A2, I'm going to remove column 2. And in A3, I'm going to remove column 3. And I'm going to replace those columns in each case with the values from the constant column, which is -20, 22, and 0. -20, 22, and 0 in each case. Now my job is to find the determinant of each of these 4 matrices. I'll write these down here: the determinant of A, the determinant of A1, of A2, and of A3. And I'll have some computations to do, which I'll probably do down here. And once I'm done, I'll still have some ratios to figure out. But let's find those determinants and we'll go from there. Now, for the determinant of A, I'm in luck because I have a row that's made up of mostly zeros. So I'll use -1 as my coefficient for the first term in working out this determinant, but I don't need to worry about the other two terms. So let me use my highlighter and I'll cross out row 3 and column 1. And my determinant then is going to be, the determinant of that matrix is made up exclusively by the determinant of this submatrix, although I am going to have to negate it because I'm multiplying by -1. So it's going to be -1 times -5 times 4 is -20 minus -6. And -20 plus 6 is -14, but I'm taking the opposite of that, taking the opposite of -14, so I get 14. And there's one more thing to consider here. I chose to use row 3 for my cofactor expansion, so the cofactors that I came up with were the cofactors associated with -1 and with 0 and with this 0, and obviously because I'm going to multiply these by 0 in determining the determinant, these two don't need to be computed because they just turn out to be 0. When I compute this one, I need to consider also that I'm taking this value, I'm taking this entry from row 3, column 1, and the position, therefore, of the entry determines its sign, and in this case, that's 3 plus 1, which is 4. -1 to the fourth power is +1, and so I don't need to change the value of 14 to -14. That is, in fact, the determinant of A. Now I need to do the same thing with the other three determinants. I'm in real luck with A1 because I have an all-zero row. You may remember from our talk about the properties of the determinant that if A is a square matrix and it has a 0 row or a 0 column, then its determinant is 0. So all I'll need to do here is note that. Now, if you don't remember that from our the property, there was a list of properties of the determinant a few videos ago, a couple of sections ago. But even if you don't remember that, it should be fairly straightforward or fairly easy to come to that conclusion, because you're going to pick the row or column that gives you the least amount of work, and this one here is all zeros. So as you begin to compute as you begin the process of cofactor expansion, you're going to have a coefficient of 0 times some subdeterminant plus 0 times some subdeterminant plus 0 times a subdeterminant. So you're going to have a product, a sum and product that adds up to 0. So even if you actually kind of start to step through the process, you're going to end up with a determinant of 0 pretty quickly. For the other two, it turns out that I have, I'm going to use row 3 in both cases because I have a row that's mostly zeros, and fortunately for me, the other value in that row is a 1. It's a -1, so I do have to be careful with my signs. But in both cases, I'm going to use that value to figure out what the determinant of the 3 by 3 matrix is. So for A2, the computation goes like this. Let me move this over a little bit. And I'll do the same thing here. I'm going to have that -1 times this determinant. And that determinant is -80 minus -66, which gives me negative. Now 80 minus 66 is 14, but it's -80 plus 66, so it's -14. And that means I have a +14. Double checking my sign here, I have row 3, column 1, 3 plus 1 is 4, -1 to the fourth power is positive, so there's no sign change here. For A3, the determinant is -1 times the determinant, -5 times 22, which is -110, minus -40. That gives me -70. And that, of course, is 70. And I'm in the same position as I was for the previous entry, for the previous determinant. So I'm in row 3, column 1, row 3, column 1. We determined that there was no sign change. 3 plus 1 is 4, negative 1 to the 4th is positive. There's no sign change here. Okay, so I have my 4 actually determinants. Let's highlight those. We have the determinant of A1 is 0. The determinant of A2 is 14. The determinant of A3 is 70. And the determinant of A is 14. The last step is to use the little ratio formula at the very end of this process to figure out what the x1, x2, and x3 values are, the solution to this system of equations. And that comes about by taking x1 is equal to the determinant of A1 over the determinant of A. x2 is equal to the determinant of A2. See what I mean about those subscripts? Everything matches over the determinant of A. And x3 uses the determinant of A3 over the determinant of A. And those are, in turn, equal to, well, the determinant of A is 14, so 14 in all three cases in the denominator. And then for A1 we have 0, for A2 we have 14, and for A3 we have 70. That gives me 0, 1, and let's see, 70 over 14. 7 goes into both of those. I have 10 over 2, that's 5. Okay, so my third value here is 5. So I can either write this as you see it here, x1 equals 0, x2 equals 1, and so on, or I can write it as a horizontal, as a point. Let's do it that way first, 0, 1, 5, or as a horizontal row or vertical column matrix. It depends on the context, depends on how the question is asked, depends on a lot of things. But this is my final answer in various different forms for this question. And that's Cramer's rule.